Okay, we begin with the vector algebra. We have more or less 5 problems today. Is a physical quantity a rational number or an irrational number? A real number. Remember, number line. There is a 0, a reference point, and unity, well, number 1. If you determine these 2 reference numbers, then if you pick any point P on the number line, it can make, you can find the real number X that makes a one-to-one correspondence with this point, physical point. That is the main issue of a real number. In mathematics, rational number and irrational number, they distinguish it because it concerns algebra. According to algebra, you cannot find a solution whose floating point expression does not terminate. Any integer divided by another integer that is non-zero, this one can be expressed, for example, as a floating point, but always this floating point expression terminates at some point, and after that, everything is a 0. However, irrational number is not the case. It does not terminate. However, in physics, we also deal with number, but unlike mathematics, physics has additional quantity called dimension. In mathematics, dimension refers to the number of independent axes. For example, a number line represents a one-dimensional Euclidean space. If you bring in another axis that is perpendicular to the x-axis, then the x-axis and y-axis, they make a plane. It is according to the Euclidean geometry, you have a two-dimensional plane. In reality, we have additional axis that is called z-axis, and we are living in the three-dimensional space, three-dimensional Euclidean space. And Newtonian mechanics assumes that the space is a three-dimensional Euclidean space. Euclidean space is nothing but the space in which Pythagoras' theorem is valid. Okay. However, in physics, there are many other dimensions. Why? These are of length dimensions each. However, in mathematics, they don't care about the dimension. This dimension is a physical dimension. They count the number of independent axes. So they say, oh, there are 3 linearly independent basis vectors. Okay, so this three-dimensional Euclidean space has 3 linearly independent vectors that are called the basis vectors. Usually we choose the unit Cartesian basis vector along the x, y, z axis. If you are living in a two-dimensional plane, you only need 2 independent basis vectors, something like that. However, in physics, we have dimensions such as length. Because we are living in some space, we are living in this nature that includes time. Without time, we cannot describe any motion. We are not living inside a picture. Instead, we are moving around, we require a time. In addition, it is not mathematical plane that is empty. In physics, our nature is filled with matter, and any matter has its own mass. So we have mass. In addition, just like the extension from the number line to the plane and the volume, we have powers, powers of length, and sometimes powers of time. For example, we have a displacement from a place to another, delta x, that represent the length. However, sometimes we are interested in measuring the velocity, that is the ratio of the displacement against the time difference. Oh, so we have time in the denominator. In addition, we are sometimes interested in the acceleration that requires additional time difference in the denominator. The acceleration is usually written in the second order time derivative of displacement. Therefore, we bring in time squared in the denominator. In such a manner, A, B, C, they do not have to be an integer. Any real number is possible, and we are living in the space of various dimensions. The existence of dimension makes it more complicated than usual mathematical problem, because first of all, we can think about an algebra. Algebra is the, for example, what's wrong with that? It's too sharp. Too sharp. Okay, good. Algebra is sum, difference, product, and division. This simple operation is applied to some number. Then we call it algebra. So when we compute the, for example, square root or sine of x, something like that, it is non-linear function. It is difficult for us to reproduce this number. However, still the algebra is useful to find an approximate value. And actually, I believe that you are familiar with the Taylor series expansion. That is a kind of algebraic approximation of nonlinear function. Anyway, we are interested in the vector algebra. Why? X is the position that is the most fundamental physical variable appearing in physics. Position, time. Using this, we find the change in position and how fast, velocity, and take another time derivative, and so on. In this procedure, this part, this is the difference between the two position vectors that is called the displacement. In here, we use subtraction. So we shall find that we must be familiar with the vector calculus. However, everything begins with algebra. So when we add two physical quantities, for example, x plus t, in mathematics, usually they use real number. A real number is indicated by an x, unknown variable, something like that. But in physics, absolutely different. X is usually displacement and position. You know, the dimensions of displacement is length, single power. And this one is time. Time has the dimension. It's a single power of time. Can I add X and T? No way. It is not defined. So as far as you are living in a dimensionless space that is called a mathematical number, then that's fine. But that is not reality. Physics is absolutely different from mathematics. Next, what is the algebra of scalar variables in physics? Okay, in physics, we have variables called physical quantity. Previously, we understood what the physical dimensions are. In addition to the dimension, any physical quantity has its own magnitude and sometimes it has its own direction. And actually, scalar variable is a spatial vector. It's not a spatial, it's a spatial vector. A point on a number line indicates a one-dimensional vector space that is called scalar. So if you express a physical quantity in units of a dimensionful physical quantity multiplied by a real number, then we call it is a scalar. And for example, we have a displacement that is a vector. This one also appears in one dimension too. However, if you extend this one into two dimensions, this vector with the same magnitude have different spectrum. If you do not know the direction of this vector, you cannot identify these and this, but they are different. They are the same only if the magnitude, sometimes it is called the length, and the direction simultaneously. Okay, so if you restrict yourself into a single direction only, this vector becomes a scalar. And if you are working on a scalar, something like time, mass, temperature, and so on, then you need to do some operation. So adding time, find the difference, and what is the half of the magnitude, something like that. These are algebra. So we need to carry out algebra. As I already told you, anything has its own dimension. So let's see. Multiplication may change the physical dimensions of a physical variable q. Okay, we have a q. And why don't we multiply this q by a number, alpha? Only if this alpha is a pure number. Pure number means any powers of length, mass, time is missing. So it is one, that means dimensionless. Only if it is a dimensionless, alpha q and q can be added. If this one has the dimension, we cannot add them up. Okay, we have velocity. That is the first order time derivative of position. And if you multiply this one by mass, what we obtain is the velocity multiplied by mass. That is the momentum, linear momentum. They look similar. They cannot be added together because they are of different dimensions. So when we want to add or subtract two physical quantities like mathematics, we have to check whether the two quantities are of equal dimensions. For example, multiplication. Multiplication is, however, always allowed. For example, even power of x is a dimension of length, then x to the power n, x to the n has the dimension of the same power, something like that. Division, except for the division by zero, it is also allowed, and velocity, displacement divided by time, density, mass divided by volume are always defined. Be careful, once you take the ratio, these numbers cannot be added arbitrarily because it is a kind of average. You say average of the two numbers, two sets of numbers, then the total average must be computed not by simply this is the average of V1 and average of V2. This one cannot be added. You can add, but it is nonsense. Third one. It's too easy. Looks too easy, but easy thing is in many cases is not obvious. We learned from elementary school the addition of two real number or integer addition, sum. You can obtain a sum. That sum is independent of order in the adding process. In many cases, in nature, especially for the multiplication, it is possible to have non-commutative multiplication. Special example is a kind of rotation. However, addition is commutative. If you learn these commutative law and additive identity, additive inverse in mathematics, sometimes it is very simple, sometimes it is a kind of headache because you have to memorize without understanding what's going on. However, you have to remember mathematics is not a pure invention. It is a it began with the carbon copy of nature. All these numbers, scalar is a 2, scalar is just a one-dimensional vector, and all of this computation, mathematical structure, is a carbon copy of Euclidean space. And Euclidean space is not the invention of Euclid itself, and Euclid copied the nature. And he made his own universe that mimicked the nature. The very basic nature of scalar and very basic nature of vector comes from the position and especially the displacement. Using this displacement vector, all of these algebraic properties of numbers derive. A strange rule is a distributive law. Distributive law involves a kind of physical quantities and another kind of physical quantities. If you learn this distribution law in mathematics, there is no difference at all. There's just pure number, real number, sum, and multiply the another real number. However, if you consider a vector space that is originated from the displacement, the story is absolutely different. You move around from place or place to here. This is a school and use a home. The way back. So this is the displacement vector from school to your home and home to school. They are opposite. This minus x. There's a restaurant. You can go there, go home and go restaurant. However, you can go this one first, or displacement is believed to be invariant under translation. You can draw any parallelogram. This is parallel and keep the length the same. Then you can move this one and then move there. So you can draw a kind of parallelogram. This one shows that the displacement A and displacement B result in A plus B, and you have another way of adding two vectors. This make a displacement B. These are parallel and of equal length, and then this is true if the space is uniform. And that is the assumption of Euclidean space. So this is not coming from mathematics book, but coming from your own experience in flat space. An extension to the associative law is you can draw a kind of cube and you move around from this point to there. There are many ways to go there. This. Eventually, from the beginning to the end, if you connect the two endpoints, these various way of adding various vectors results in the unique value. Uniqueness in mathematics is very useful because you do not have to express something in a redundant way. What about the vector? I already explained in detail for the commutative law and associative law and finding additive identity and find the additive inverse to result in the additive identity. And associative law, the distributive law, for the vector addition, there are two kinds. A vector can be multiplied by a scalar. In mathematics, these scalars are just the pure numbers, but in physics, these scalars does not have to be a number. For example, if you have velocity and if you have mass, I can multiply. And if two particles are of the same velocity, I can multiply the sum of the two masses together. And actually, this is the total linear momentum, something like that. So multiplication of the two physical quantities, you should always be very careful about the physical dimension.